Hello everyone. In this lecture, we will talk about a new neural network architecture, recurrent neural network. This lecture is built based on the two reading assignments. One is a Stanford CS230 RNN sections. The other is famous block from Cola. There are different forms of data for machine learning study. Up to now, we have studied image classification. The other popular type of data is sequential data. For example, the sound, audio, or the streaming of the image. How can we apply machine learning techniques on sequential data? This will be the major topic for this lecture. First, let's go through some famous type of the RNN application. In this picture, shows a one-to-one mapping. We start from an input vector with a machine learning weight. We can calculate the output vectors. The famous application for this architecture is binary classification problem. For example, you have an image here, and we want to determine the output is pass or fail. For RNN, one of the famous application is many-to-one. You have a different timestamp of the data. For each time step, you have a specific input vector. You can apply to the matrix weight to determine the output. You could apply this kind of many-to-one architecture to sentiment classification. You can determine the sentiment or the feeling. For example, here is a sentence, there's nothing to like in this movie. We want to apply this many-to-one classification to determine this is 1 star or 5 star, and this sentence obviously for us is quite a low rating. There could also be one-to-many. You have one input vector, you can generate a sequence of the output vector. For example, this is an image. We would like to generate a sentence is a series of the vector. A man is running. The RNN architecture is capable of doing such a one-to-many classification. You can also do many-to-many. You have many vector input, several vector output. A famous application for this is machine translation. Here is a sentence structure in French. We would like to have a machine can automatically to translate to English. One particular thing is that this many-to-many doesn't have to be word-to-word, because the grammar for different language, they could have a different ordering of the words, of the vocabulary. Therefore, this many-to-many can map from a different dimension of the input vector to another dimension of the output vector. Let's try to go through a basic structure of the recurrent neural network. For a typical neural network, a list of the input structured data, it's input vector, and after matrix application, a set of output vector. You have a weight function can transform the input vector to the output vector. The sequence of data have a special property that the update of the next output could depend on the information from the previous state. We can think about attach to the next output calculation should contain the information from the previous state output and also the second input vector. The general setup of this transfer function is input vector. The function also understands how to react based on the past memory. And past memory is the state memory cell from the previous network calculation. The final output will depend on both. If you continue to apply this architecture, you could have a different time step of a set of the calculations. You can denote such of the series of the calculation as a recurrent cell. A basic concept of the RNN will take a series of the input vector and try to apply the same recurrent cell, provide the sequence of the output. Given this, we can define P of such a recurrent neural network is the calculation of the cell state. We want to apply a recurrent relation every step to process a sequence. To get each of the cell state, we want to define a function with weight matrix W. Weight matrix W depends on the input vector, the information from the old state. One particular feature of the recurrent neural network is we want to apply the same weight function and with a set of parameters used for every timestamp. The cell state here is updated at each time step t as the sequence is processed. This is the way that we can use a smaller number of parameters to model the behavior of a recurrent neural network. Now let's try to go through the math equation to implement such a recurrent relation. First, we start with input vector. We need two weight matrix and one bias vector to update the hidden state. This cell state will take the input from the previous state and times this weight matrix WAA plus the input vector times the input weight matrix and add a bias term. Then this can update the hidden state for the next cell state. Once you have defined the next cell state, the output vector can be computed from the output cell state times the WYA, this is the weight matrix, and plus the bias vector. The output of the hidden state and also the output vector will go through two activation functions, G1 and G2. And these introduce the linearity of the neural network. In summary, we can use this flowchart to describe one recurrent cell. So for each time step t, the activation A is the cell state, can be the activation AT is a cell state output. The activation cell state AT and the output vector YT can be computed from this input of the previous cell state times the WAA matrix and plus the input vector times the WAX matrix with a bias vector BA. We can apply activation function G1 and this gives us the cell state output. From the cell state output, we times a matrix WYA and plus a bias vector BY pass to another activation function G2. This will give us the output YT. AT will pass to the next recurrent state together with the next input vector and compute the next output vector YT plus 1. Such recurrent relation just continue to apply. The same weight matrix here and also the bias term here and activation function will be applied to every single recurrent cell. What are the pros and cons of a recurrent neural network? It is good with a possibility of processing input of any length. You can imagine you can attach variable length because a sentence of the same meaning could compose of different number of the vocabulary in different language. How you can map between different language? One of the key things that you have to solve the problem to take different input of the length and to generate different lengths of the output. Because we use the same recurrent cell, therefore we can do the calculation taking into account historical information. We have the weights can share across different time steps. This can have a manageable number of the parameter of the weight. However, there's also the drawback for the RNN computation being slow because you have to repeat the same cell calculation multiple times. It's difficult to access information from a long time ago. If you have a long sentence, when the first word probably to the end of the sentence, the importance of the first word might fade out, and it cannot consider any future input for the current state. To solve such a drawback, there's a new architecture, for example, attention mechanism, which is used for the transformer. And this is an improvement for the RNN. It's beyond the scope of this lecture. We would like to encourage you to do the study beyond the curriculum. Now let's take RNN in practice. Neural network is a numerical problem. Therefore, we need a way to map our questions into numerical questions. And this is called encoding. For example, you have a sentence or an article composed of 10,000 words. You can use one-hot encoding. Each of the words can be encoded with a list of 0 vector, but with only one index flagged with 1. With such encoding, you can have a mapping of the individual word to each individual index. Then you can use this index as the input vector as well as the definition output vector to do the machine learning calculation. The other practical implementation of RNN is the loss function calculation. Let's take one example. We have a sentence here, and we like to predict this blank word. We have a 14-word input, and we want to make a one prediction output. We can define the loss function. The ground truth is the output vector, and the predicted output. We want to minimize all the loss coming from each of the training sample. In order to compute the optimal weight, the gradient descent have to be calculated with respect to every single weight parameter. And these weight parameters will propagate again through the time. It will back propagation through each of time stamp from the current one all the way to the oldest time stamp. From this, you could observe two issues. One, you could have a vanishing gradient issue. The gradient could be small, so when you propagate through time, the more number of propagation you have, the smaller the number of gradient to get. And this might lead to an issue that you cannot calculate appropriate gradient descent. To resolve this problem, we can use a gated structure to control the flow of the output. There are three famous activation functions has been used to design the gate. The sigmoid will translate data from 0 to 1, and hypertangent will regulate data from -1 to 1, or the famous rectilinear unit. It can regulate the number to 0 and linear proportional with the positive value. It will regulate the value to 0 for negative input and linear proportional to the input for the positive value. Other than vanishing gradients, we could also have an issue of exploding gradient. When the gradient is big, you propagate through multiple cells, the gradient will become too large. In that case, you cannot calculate the gradient. The trick to resolve this issue is gradient clipping. We could define the maximum number of the gradient. So when gradient is greater than that critical value, we just clip into a constant number. This can provide the stability of the gradient calculations. Here are four major types of gates. A gate is computed using a sigmoid function over a set of calculations based on the weight matrix times the input vector and the propagation matrix times the input cell plus the bias vector. The four major types of gate, the first one is an update gate. The role for update gate is to determine how much path should matter now. If the path memory is not interesting to determine the state of this current cell, then we want to forget those irrelevant information. The relevance gate will drop the previous information as an input to compute the next information. The forget gate can determine whether a cell is relevant or not and erase the cell. The output gate will reveal how much should be forward to the output in this cell. With these gates, we can construct a famous long short-term memory RNN architecture. This is one of the most popular RNN architecture. We will try to focus on the discussion of LSTM. There are four steps for LSTM: forget, update, store, and output. The first gate applied is the forget gate. The forget gate will take the previous state cell and keep a parallel set of the coefficient to determine whether the relevant part of the previous state should be considered and passed into the next calculation. As the second step, we will select the update cell state value. If a particular cell is not important, then it will not be included into the calculation. We will further propagate so relevant new information into the cell state. And this calculation will use a tanh of the propagation of the state information from the previous two gates. Then finally, we have output gate, which control the information to be sent to the next timestamp. With such calculation, we can complete a LSTM cell. Using these four gates, we can deal with the vanishing gradient problem encountered by traditional RNN. Because now we have control of the information flow, we only keep the relevant information to discuss the problem. In summary, for LSTM, it can maintain a separate cell state from what is outputted. It uses gates to control the flow information. First, for get gate gets rid of irrelevant information. The update gate will select the cell state for calculation. Store gate will only keep relevant information from the current input. The output gate returns a filtered version of the cell state. The bit propagation through time with uninterrupted gradient flow is also implemented for the LSTM. We can use this sentence example to illustrate the advantage of LSTM. I grew up in France and moved to the United States, therefore I speak. From our interpretation, we naturally will say this blank word should be a France, because the person grew up in France, even though just moved to United States. It's quite likely the person speaks French. But if the short memory carry more, United States is more close to the blank word. This is not necessarily the most relevant information we want to remember. If we don't have a mechanism to determine the importance of the word in the sequence of the sentence, United States is more close to the blank word, we might misidentify this language output as English because United States is more close to the blank word. Therefore, LSTM can introduce a capability that in terms of relevance, friends grew up, these pair together have more weight than the location, which is closer to the blank word. Using LSTM, we can control the information flow to make the final prediction. In this week, we'll work on the hands-on activities based on LSTM. Up to now, we have practiced jet identification problem when you have proton beams produce the jet or quark, which can shower into hadrons detected by the calorimeter. The calorimeter can be flattened out, and we can build the jet image. Each of the cells here represent the energy deposition of the particle flow inside a jet. Using convolutional neural network, we can develop a very nice classifier to determine top quark from the QCD quark. Instead of convolutional neural network, we can use LSTM to solve this many-to-one problem. Each of the input sequence can be a particular row of the image. The first input vector is the first row of the image. The second input vector is the second row of the image. And we can continue to pass the n row of the vector into the RNN architecture. This paper is one of my first papers showing the LSTM application. We can use a similar style of the loading of the data. Instead of using convolutional neural network, we can show LSTM architecture also provide very good classification power. An even nicer way to do it is to look at the nature of the jet shower. The process of this jet fragmentation and hadronization is actually a series of the gluon radiation and the quark splitting from the gluon. The final hadrons detected by detector is the end product of the proton shower. Therefore, we can imagine the sequence of these final hadrons can represent a particular showering process of the jet development. We can apply this concept to construct an RNN architecture. Each particle is a constituent of the jet. It could carry information, for example, the force vector, the charge of the hadrons. They can be passed into an RNN architecture, and each particle is an input set of the vector. Through the RNN propagations, output can be used to build a classifier with one binary classification output. This can nicely capture the nature of the tree structure of the jet. Alright, this is the end of the lecture today. Here are more references for you to study the RNN, in particular the understanding of the deep sequence modeling. Welcome to study this material. Enjoy your hands-on lab this week.